Alright, the first real video of Chapter 4 here, we're going to be talking about one specific type of experimental design. And so first, we're going to jump into part of the reading that you should have already done here. Before we actually design some experiments here, we need to keep in mind of some important facts. Number one, it's always nice to have a control group when you do an experiment. And the purpose of our control group was to reduce any type of bias that may happen from groups that do get a treatment. Number two, we want to randomize. We want to use chance. We don't want one group to have a specific advantage over another because maybe psychologically in the back of our mind we want to see some treatment succeed when in fact it may not if we would have used a random sample to get our individuals. So this is what we did in the first part of the chapter. And then it's always nice to replicate each treatment on many units. You wouldn't just want to use a treatment on one individual randomly, but it really helps to have many individuals get that same treatment. And the most important part of that was that larger sample sizes will always yield more accurate results. Okay, so again, you don't just want to stick with sample sizes of 1 or 5, depending on exactly what you're dealing with. But the larger the sample size, the better. It'll help reduce chance, variation, and error. So what we're going to talk about today is just the completely randomized design. And then we'll talk about two more specific types of designs in the next video called a matched pairs design and a randomized block design. So in a completely randomized design, this is the equivalent of a simple random sample. Okay? Basically, you're going to have some sort of treatment, you're going to randomly assign it to some people, you have a control group, and in the end you compare to see was the treatment group really better than the control group. So that's essentially what a completely randomized design is. It's the equivalent of a simple random sample, but now in terms of an experiment. So the first example we're going to look at here says a food company assesses the nutritional quality of a new instant breakfast product by feeding it to 15 newly weaned male rats. The response variable is a rat's weight gain over a 28-day period. A control group of 15 rats eats a standard diet but otherwise receives the exact same treatment as the experimental group. Okay, again, that is key for a control group, is that essentially they get the same exact stuff, except the treatment is tweaked just a little for the treatment group versus the control group. You want all of the rats in your control group and your treatment group to be about the same as each other, and that's where the random assignment comes into play. So first, how many factors are there? We have one factor, and that is the diet. Okay, we're feeding this new instant breakfast, and that is the one thing we are experimenting with. And we have two levels of our factor, that being the instant breakfast and the standard diet that our control group will be receiving. How many experimental units are there? Well, we have 30, because we're going to be feeding the instant breakfast to 15 rats, and then we're also going to use a control group of 15 more rats to get the standard diet. So in total, we have 30 experimental rats to deal with here. What specifically are our experimental units? Those are our newly weaned male rats. So if you wanted to be super specific, you could say newly weaned male rats are the experimental units, or you could just say rats in general. How are we going to label them? Well, since we have 30, we could say 01 to 30. You could say 00 to 29. I mean, you could even go on the other end of the spectrum here and say, 71? No, 70 through 99. That would be 30 numbers. So it really doesn't matter which 30 numbers you pick. Typically, you start from the very beginning. Now, to use line 110 to randomly allocate the rats into two groups. Here's our scheme, if you will. We're still doing a scheme here. We're going to ignore repeat rats. It makes no sense to potentially use one rat in the treatment group and one rat in the control group. So we're going to ignore repeats. We're going to ignore the number 00, since we started at 01, and numbers higher than 30. We're going to read two-digit numbers at a time until 15 rats have been selected. Those first 15 rats, they can go in our treatment group, and then the remaining 15 rats can just go in the control group. Or you could switch it around and say, well, I want my first 15 to go in the control group, and the leftover 15 go in the treatment group. It really doesn't matter since the rats have been randomly selected. Now, if I were to use line 110, these would be my 15 rats I'd come across. If you want to double check me on this, you certainly may. Just keep in mind I'm starting on line 110, and I need to follow my scheme exactly the way it is. Group 2 would just be all my other rats. So I just didn't specifically say like rat 01. I can see 02's here, 03. So I didn't specifically label out my 15 that didn't get selected from the first group. That's fine. Now here is the new part, if you will. This is designing our experiment. First, we started out with our random assignment. We had to get our rats. So here's the randomization part of our experiment. Okay, and so we randomly split up our two groups, our treatment group and our control group, into 15 and 15. So you always start off with randomization with your experimental design. You split them up into groups randomly, and then from each group you give them the treatments. So here's our new instant breakfast treatment, and then here's our control group down here that got the standard diet. So here's our explanatory variable. And then at the very end, we come back and we want to compare the weight gain between our treatment group, our actual treatment, and our control group. And this is looking at the response variable. Okay, so this is the overall design of a completely randomized design. You start out with randomization, split them up into groups, give them their treatments, and in the end, come back to compare. So when doing an experiment, we hope to see a difference in the response so large that it is unlikely to happen just because of chance variation. All right. Now, when we come back and we compare the instant breakfast to the standard diet, there's probably going to be a difference. Okay. Now, is the difference large enough that the reason why there's a large difference is because of the instant breakfast? Because if we give them a standard diet, that's our baseline that we're comparing to. Is the standard diet truly different than the new diet? And so there is a chance that if the difference is small enough, that it's just chance variation. It could just be that the new diet is maybe somewhat different than the standard diet, that it did produce a little bit of a difference in the weight gain. But if it's not large enough, we can't say that definitively that it was the new diet with the instant breakfast that caused the significant weight gain. So if the difference is larger than what we would expect to see due to chance variation, we're going to call our result statistically significant. Okay, so this is a key word phrase that we will be using. So if we do believe that our treatment is definitely causing a significant change, we will call that result statistically significant, that it is definitely different and it has caused a new result to happen. All right, another example we're going to look at. It says a manufacturer of food products uses package liners that are sealed at the top by applying heated jaws after the package is filled. The customer peels the sealed pieces apart to open the package. What effect does the temperature of the jaws have on the force required to peel the liner? To answer this question, the engineers prepare 20 pairs of pieces of package liner. They seal 5 pairs at each of 250, 275, 300, and 325 degrees Fahrenheit. Then they measure the strength needed to peel each seal. So use a diagram to describe a completely randomized experimental design. Okay, now we're going to skip over, this is basically what I want you to do, is what we did here on part F. We're not going to have to worry too much about the A through E part of this piece. So again, for this part, I just want you to make the diagram. So first we have our random assignment, which can be abbreviated RA. And I've got 4 treatments. Okay, I have one factor, and that is temperature, but I have 4 levels, and those are my 4 different temperatures here. So from my random assignment, I'm splitting this up into 4 groups. and it said I had 20 pairs of pieces. So each group gets 5 liners. And so in each group of liners, here's our 4 treatments at 250, 275, 300, and 3 1/4. And then once we have applied our treatment, now we're going to come back together and we're going to compare the force that was needed to peel each liner. Okay? We don't know if necessarily that a higher temperature makes it tougher to open a liner, or maybe a cooler temperature is tougher to open. So they want to try to find a force that's high enough where the food just won't come through the liner during the shipping process, but they don't want it to be so tough that nobody can really open it, or only like the world's strongest man can open it. So again, this is our completely randomized experimental design. Random assignment into groups, give each group a treatment, and then in the end come back and we get to compare. Now, the very last part here is the actual scheme piece of this. So use table B starting at line 120, and you have your random number table in your back of your formula sheet to do the randomization required by your design. So I want you to write the scheme. What numbers should we use? How many numbers should we read at a time? What numbers should we ignore, skip, etc. And then go ahead and actually do it. Tell me which 5 numbers are going to be in the 250, which 5 numbers are in the 275, which 5 are in the 300, and then your leftover 5, you can just say, go in the 325. Okay, so this is what we will check and discuss tomorrow during class. So that is all. Adios and goodbye.